In this video, we'll be looking at a review of how we factor by grouping. We'll be looking at difference of perfect squares and how we find the roots and why that works for our quadratics. So remember that we always want to look for our GCF first. It's the first thing we learned when we talked about factoring, and that always applies no matter what you're doing. So you want to make sure that you're focusing on pulling that out of each expression before you factor. So we have 2x squared plus 12x plus 16. The greatest common factor across all of those is positive 2. If we were to factor that out, then we could go ahead and get x squared plus 6x plus 8. And so if we were to continue factoring this, we would get 2 times x plus 4 times x plus 2. And these would be our three factors then. 2, x plus 4, and x plus 2 are all those factors, and we would use those to help us solve. In our next one, we have a GCF of 3 across all of these, and so we would be left with x squared plus 6x plus 9. And so the reason we're looking for that GCF first is to really avoid having to do too much in the way of our grouping method. Otherwise, we'd be looking for factors of 3 times 27 that add up to 18. While it's doable, sometimes that might just be a little bit more work than we really need to do. So by doing this first, that is helping us fully factor and ensure that we are getting the correct answer. We would go ahead and break this one up into 3 times x plus 3 times x plus 3. And that would get us our fully factored form of the second one. And our GCF in this last example is a 2, and we're left with x squared plus 10x plus 16. And our two factors there that add to 10 and multiply to 16 would be 2 and 8, so x plus 8 and x plus 2. And that would be our fully factored form. So looking for that GCF first is just going to save you a little bit of grouping work there. We're going to focus on what our difference of perfect squares is. So what you'll notice here is that we have x squared minus 49. We're used to seeing trinomials. This is just a binomial. But what we see is that it does have an x squared value. So we could solve this by saying if we wanted to know what x was, x squared minus 49 would equal 0. So we would get x squared equals positive 49. Then we would take the square root of this, and the square root of 49 would be plus or minus 7. So what that tells me is that the two solutions here would be coming from x plus 7 and x minus 7 if we were going to figure this out. So how does that work with what we've learned? Well, we have x squared and we have negative 49. That's our leading term, so the ax squared part and the c term. We're missing that bx term that we're used to seeing in our quadratic trinomial. So what this really is telling me is that I could break this up into positive 7x and negative 7x, because if you notice, we have that positive and negative 7 there. We're looking for our factors of negative 49 that add to 0 then, essentially, because if you were to add these two together, you'd be left with 0. So kind of that missing piece right here that we're not seeing. If we were to use our grouping method on this, we could check and we would see, well, the GCF of the first part is x, so x plus 7. And then my GCF of the next part is negative 7, so we would have x plus 7. And that leaves us then with, remember what we learned with grouping last time, we have x plus 7, and we were distributing that x minus 7 to it. So that x plus 7 and x minus 7 then, if we were to FOIL that, would get us all the way back to our original expression of x squared minus 49. So now that we've kind of talked about why this works, we can apply this then kind of as a shortcut. So our difference of perfect squares is going to be when you see x squared minus a term a squared, and that's going to equal x minus a times x plus a. So when a squared is a perfect square of that whole number a, or that integer a, we can rewrite it as this fully factored form. So our a squared value here would be 8. So if we were to rewrite this in the terms of, we don't need an a, in the terms of what we kind of just showed up top, 64 is the same as 8 squared. So this is really the same as x squared minus 8 squared. So if we apply this to our rule, it should be that x minus 8 times x plus 8 should get us back to what we started with. Now remember, we can always check. X squared, we have plus 8x, minus 8x, and minus 64 when we FOIL this, and our two terms in the middle become 0, and we're left with what we started with. So there is our shortcut. So looking at our next couple, we have x minus 3 and x plus 3, since the square root of 9 is plus or minus 3. And for 5x squared minus 500, first thing, remember, we want to look for that GCF. Noticing that 5 is a common factor across both of those gets us, 5 times x squared minus 100. So we can break this up into x minus 10 and x plus 10. So this is just something that you want to try to keep in mind. Of course, you could rewrite it the way we broke up the first one and see what you could add those numbers up to make that 0 term in the middle. But if you can remember your difference of squares rules, then it's going to save you a little work and you can apply it to this shortcut. Now, something that we've been doing throughout our factoring unit so far is we've been solving for what the solutions of x are. And so the reason that this is working is because we're actually figuring out when y equals 0, what is our answer of x? So where are we on the graph when y is 0? What is our x value? So the reason that this happens is coming from what our shape would, or what our graph would look like if we were to put it on the coordinate plane. So the first thing I want you to do is pause the video and figure out all of your y values, or f of x values, for the function f of x equals x squared plus 3x minus 4. Plug in -5, get your answer, and then plug in -4, and so on. Press play when you're ready to check. Our values that we end up getting are 6, 0, -4, -6, -6, -4, 0, and 6. So you'll notice that they kind of like repeat each other here. So when we go ahead and put this on the graph, we have -5, +6, and then -4, 0. We've got -3, -4, -2, -6, -1, -6, 0, -4, 1, 0, and 2, 6. When we connect all these all the way through, we end up getting a parabola, and it's that U-shaped graph that goes on forever. Because our leading coefficient was positive here, our parabola is facing upward. So it's kind of that U shape that is continuing forever. And when we've talked about parabolas before, parabolas are going to have at least one, but most likely two, depending on where it is touching the graph. In this case, because it is graphed and it has two places where the graph touches the x-axis, that means that it's going to have two solutions for x. So when y equals 0, we are going to have a solution. So -4, 0 will be a solution, and 1, 0 will be a solution. And that's right here on the graph. So the point -4, 0 and the point 1, 0. So if we were to take this expression, x squared plus 3x minus 4, and set that equal to 0 like we've been doing when we've been factoring trinomials and solving for their x values, we're going to be looking for factors of -4 that add to +3. Well, that would be 4 and -1. So that means that our two factors here would be x plus 4 and x minus 1. Those are equal to 0. And remember, when we break these up and set them equal to 0 to solve for x, we end up getting that opposite sign. So x equals -4 and x equals 1. Well, that's exactly where we had just seen our graph, or a parabola, touch the x-axis. So when y equals 0, we get our solution. And so that's why we've been setting our trinomials equal to 0 and been able to factor to get those two values for x. That's what it would look like graphically. So this is another way then you could check your work when you're solving something where you need to factor. Graph the function, see what the x-intercepts are, and that should be the solution to your quadratic. All right, so we're going to apply our factoring rules, including grouping and difference of squares, to these geometric examples. So first off here, we've got two lines that are parallel, They're being intercepted by this transversal line, and we see that we've got some alternate exterior angles happening because they are on opposite sides of the transversal outside of the parallel lines. Since the lines are parallel, we know that these two angles can be set equal to each other. So 3x squared plus 11x should equal 2x squared minus 18. Remember, whenever we see an x squared, we want to set equal to 0 to try to find the solution. So subtract the 2x squared minus 18 from that side, and we'll end up with x squared plus 11x plus 18 equals 0. We have a leading coefficient of 1, so we can just find factors of 18 that add to 11, and that would be 9 and 2. So x plus 2 and x plus 9 are both equal to 0. And when we solve our equation for both of those, we get x equals negative 9 and x equals negative 2 as our two solutions. Now, when you go ahead and you plug in your values of negative 9 and negative 2 for x back up in the the diagram here into their two angle expressions, when we plug in negative 9, we end up getting 144 degrees for both of these. So while it might not be drawn to scale, that's a reasonable value for those two angles there. When we plug in negative 2, we get an expression that's equal to negative 10 degrees for those, and negative 10 is not a possible angle value. So negative 2 is actually a solution that doesn't work for our geometric example, even though it was a solution to our quadratic. So the only answer for this, because of geometry rules, will be x equals negative 9. Go ahead and pause and press play when you're ready to check the next problem. Here we have angle 1 and 2 that are between two parallel lines. It told us that K and L are parallel right here. And so these two are both on the same side of the transversal and inside the parallel line. So these are consecutive interior angles. So they're not congruent, but they are supplementary. So we can take x squared plus 94 plus 5x plus 62 and set it equal to 180 total. At this point then, we're going to combine like terms and set equal to 0. So we get x squared plus 5x minus 24 equals 0. Then we have x plus 8 and x minus 3 as our two binomials here. Since we had that leading coefficient of 1, we can use our shortcut. And we're left with x equals negative 8 and x equals 3. When we plug those both in to our expression here, we get an angle pair of 103 and 77, which are supplementary, and we get another angle pair of 158 and 22. So two possible solutions that actually make sense for what we're talking about. Those two pairs of angles could both exist in this diagram. So either of those are solutions to our problem. Next up, we have the angles in a triangle that are given. And remember, with our angles of a triangle, they always have a sum of 180. So we're going to need to add all these together and set it equal to 180 degrees. So we'll take 2x squared plus 9x plus 70 plus 117 and set that equal to a total of 180 degrees. When we simplify, combine like terms, and set equal to 0, we're left with 2x squared plus 9x plus 7 equals 0. Now we don't have a GCF, and we have a leading coefficient that is not 1, so we need to take 2 times 7, which is 14, which tells us that's what we want factors of, and those factors need to add to 9. So the two numbers that will work for us there are 7 and 2. That means when we rewrite this, we can take 2x squared plus 7x plus 2x plus 7 set equal to 0. And remember, all we're doing there is using our grouping method and saying we're going to rewrite 9x as 7x plus 2x. So at this point now, we're splitting up our equation into kind of two equal parts here, where we are going to then factor out the GCF. So we're going to take x out of the front and say we'd be left with 2x plus 7. And in the next half, we already have 2x plus 7, so all we're multiplying by is positive 1. So what that leaves us with then, once we set them equal to 0, is x plus 1 times 2x plus 7 equals 0. And our two solutions for x then become negative 7 over 2, and x equals negative 1. And those are our two solutions here. Now when we plug them into our expressions above, just to make sure that they make sense for our geometric models, we get values of 24.5 38.5, and 117, and all of those do add to 180 and are making sense for the angles in a triangle. And then in the other set, when we plug in our -1, we end up with 261 and 117 again. So those three angles also are going to be making sense for our triangle diagram. So both of these x's are solutions even in our geometric application. Go ahead and pause and try the last one on your own. In this last one, we notice that they are complementary angles, so we need to set them equal to a sum of 90 degrees. Remember, supplementary is 180, complementary adds to 90. So we set this equal to 90 degrees when we add them together, and then we're going to try to set our whole equation equal to 0 in order to solve. What that leaves us with is 9x squared plus 27 equals 0. And right away I can tell, okay, well I only have 27x. I only have two terms this time, but I do notice that they both have at least x and a factor of 9 in them, so we can factor out the GCF. So 9x will equal x plus 3, and that's set equal to 0. So that means that our two equations that we can break this up into are 9x equals 0 and x plus 3 equals 0. So x could either be 0 or x could be -3. Now when we plug this back into our diagram, if we plug in 0 for x, that means that this angle is 0 and this angle is 90. And while 0 and 90 do add up to 90 degrees, it's not two different angles because an angle of 0 wouldn't exist. So that one's not going to make sense for what we're talking about. When we plug in the value of -3, we end up with 81 degrees and 9 degrees. Those could be the measures of two angles that are complementary. They add to 90 and they are both positive. So that one works for our geometric application.